DS900 series light flyer. Please note the screen behind me and above me is the primary screen with our first iteration of the original model, and on the secondary screen to the left is the final design for the preliminary phase. I'll now introduce the team members. I am Michael Oliveira, the DTO for Perdix Aviation. Up front here, I have Kevin Garcia. Over to the right is Russell McCaleb and Cassie Lukey. For a brief overview for what we're going over today, is going to have a brief background information of the core structure of the preliminary phase and the detail phase, and then mission specifications that were calculated and done during the preliminary phase, basic aircraft description, the model construction for the wind tunnel, and then wind tunnel test equipment, some stability analysis, followed by performance verification analysis, model modification, stability analysis, and then some performance analysis, followed by structures and some cost analysis. Now for some background information. So management from Perdix Aviation came down and handed down to the top engineers oh, yes, sir. Yeah, they handed out some requirements. They decided they wanted to enter the light sport aircraft industry. And so they give us all these stipulations. So I was going to go over the prelim phase is, last semester, we had some weight estimations followed by some preliminary sizing and conceptual design. And then we had a final iteration, which is shown on the screen above me. And then we went to the design phase and we built a test plan, built a model, put it in the wind tunnel, and modified the model, and tested it again, and then did some structural analysis. Now we go to specifications. The specifications for this light sport aircraft was it had to be able to carry 2 people and fit in a 30-foot trailer to be transportable, and it had redundant safety systems. So it's a safety thing. It's happening a lot on new aircraft. And the cost of this aircraft would be relatively cheap at $25,000 and it weighed 900 pounds. For the performance requirements for this aircraft, it had to be able to take off in 200 feet or less and operate at an altitude of 6,000 feet doing 50 knots and fly there for 2 hours. And notice to the secondary screen is a basic flight profile of what you would see with this aircraft. Now we go to aircraft description and performance. Description, in the preliminary phase, we came up with a single engine tractor configuration for its efficiency over a pusher configuration. The high rectangular wing was chosen for its inherent stability characteristics and docile stall characteristics. And the leading edge slot and the slotted flaps were chosen to help you get off the ground that required 200 feet, which is pretty difficult to do. And then the trestle landing gear was chosen for its ground stability while taxiing. To the calculations in the preliminary phase, we came up with a cruise velocity of 93 knots, a stall speed of 34 knots, with a rate of climb, an acceptable rate of climb of 1,200 feet per minute, and it was able to meet all the requirements and fly 230 nautical miles while flying for 2.3 hours. And I'll hand it off to Kevin Garcia for model construction.
Thank you, Mike. My name is Kevin Garcia. I'll be going over the wind tunnel construction for the DS900 series light flyer. So we started out with an initial CAD model. We needed some sizing for that model. There's 5 parameters that we went through in order to get that initial sizing: wind tunnel blockage, wall effects, overall structural integrity, and getting the mount right, and an overall cost. Our cost came out to about $579, which are less than our $1,000 required. Balance limitations: we need something that would produce 40 pounds of lift. It doesn't produce nearly 40 pounds of lift at what we tested at. Structural integrity, so we can get rid of any aeroelastic effects. We can get a size where we can fit some 1/4 inch, 1/8 inch rods in the structure. So like I said, we wouldn't get any aeroelastic effects. Wall effects, we need something less than the 32 inches for the 45-inch tech section, which would give us 7 inches on each side to negate wall effects. And an overall blockage of less than 7%, and we calculated ours to be 5.68%, which met that specification. On the secondary screen, you can see a ghost view and the internal structure of the DS900. It uses 1/4 inch and 1/8 inch rods in order to maintain structural integrity while we're testing. On the primary screen, you can see a exploded view of the DS900 with its many modular parts. This was designed so that we can take off the wing, take off the horizontal and vertical tail feathers for different testing configurations, while also being able to modify parts later in the course. On the secondary screen, you can see an estimation for the overall cost of the model It was based off $5 per cubic inch with an estimated cost of $579. This is all preliminary cost. The model was fabricated with the 1200 ES 3D printer, Perdix Aviation plastic with a resolution of a 1/100th of an inch. This allowed us to build the 1/12 scale model of the DS900 series. It was put in the line bath for approximately 48 hours. It took about 135 hours to actually print the model. 20 overall individual parts for the original model with a final cost of $532. Model assembly and finishing. We went through, we took out all the parts from the lab bath, let them dry out. We started honing and smoothing all the internal surfaces for the substructure. While this was going on, we worked on the internal substructure, cut all the parts that we needed in order for them to fit properly. We went through and made some miscellaneous parts like the nose gear seen on the primary screen and the support for the main gear. On the secondary screen, you can see the overall initial model with some of the steel structure in there for the tail feathers, the vertical and horizontal, and the mounting point for the empennage and the front cowl. Continuing with the model assembly, we went through, filled and sanded, followed by filling and sanding in order to obtain the right smoothness for the wind tunnel model. Then we went through and painted it with black spray paint, finished with 1,000 grit sandpaper to get, like I said, the smooth finish. You can see on the primary screen the detail for the overall main landing gear, so it can support itself. You can see half of the wing where we can slide out the wing and put it back in order to, so that it's modular. We can test different configurations. On the secondary screen, you can see the overall completed model in its rough state. On the primary screen, you can see the completed fuselage primed and paint, or just primed right now. A few details: we added the struts and the main landing gear in order to get a fully detailed representation of all the drag that we would have on our aircraft. Because struts and main landing gear cause a lot of drag, we figured out. Model structural integrity verification. We needed to ensure that the model wasn't going to have any extreme aeroelastic effects at the wind tunnel speeds we were running at. So we calculated, based on the lift equation, to produce 40 pounds of lift, it would need 150 feet per second. The wind tunnel speed would need to be that. There's minimum tip deflection about 3/100th of an inch. We tested when we loaded it at 40 pounds. We loaded it at the mounting plate where it would be loaded on the actual pyramidal balance. And the horizontal stabilizer, there was little deflection, and we determined it would be structurally sound to run in the wind tunnel. Now I'll go over some wind tunnel and testing equipment we used for the DS900. The wind tunnel used was the Tracy Doryland closed circuit wind tunnel, as can be seen on the secondary screen. It's a 32 by 45 cross section with a maximum test velocity of 330 feet per second. Barometer, thermometer to get all the conditions we need in order to determine density, those kind of things out of when we were testing. The testing equipment, we used a 6-component pyramidal balance along with the LabVIEW test software in order to get all our coefficients and needed data to verify our performance. The wind tunnel model, of course, was used, and a camera in order to document all of our tests. As you can see on the secondary screen, we have the model mounted on the 6-component balance and a screenshot of the LabVIEW software that we used. The testing configurations that we had were a full configuration, a tail off, and a fuselage only configuration. All of these went through an alpha sweep of -6 to 25 degrees and a beta sweep of 0 to -10 degrees. We went 0 to -10 degrees on the beta sweep instead of 10 to -10 because the aircraft is symmetrical. We did flow visualization as well with a complete configuration because it wasn't necessary for the other configurations. And now I'll hand it over to Matt McHale for our performance verification analysis.
Thank you, Kevin. As you stated, my name is Matt McHale. I'll be going over the performance verification analysis of the original wind tunnel model. First, on the primary screen, I would like you to note this is the tufted model, complete configuration that we tested at 0 degrees angle of attack. And as you note, the motion blur on the tufts on the aft section of the fuselage, there's a quite significant amount of motion on those tufts, which we'll go into further in a few minutes. The next image on the primary screen is the stall that we saw at 21 degrees angle of attack. You can note it on the top surface of the wing with the separation bubbles, as well as the horizontal tail. The flow is still attached on the top surface of the wing. And then there's a top view of the total stall of the aircraft at 24 degrees angle of attack, where we notice the stall characteristics going from the root of the top surface of the wing and progressing outwards towards the tip. And the top surface of the horizontal tail is now completely solid with the reverse tufts. And so we configure this as the total stall and where the horizontal tail is pointed out. Next is the beta sweep. This is at negative 10 degrees flow visualization. You can note again on the aft section of the fuselage, there is motion blur on the tufts. This is the aft right section with the negative 10 beta sweep. And once again, this also notes the significance of the fuselage drag contribution and also in terms of stability and control. This is a top view of the negative 10 degrees beta sweep and the back right section of the fuselage. You can note the tufts once again migrating towards the back right section and creating a sense of separation and motion blur as well. So from this data, or from this wind tunnel analysis of the original modification, we were able to find and compare the preliminary design results to the original model. And the original model produced a significantly less drag, which was actually to be as expected. Lift, which is actually to be as expected. However, the CL max that we were able to achieve with the original model from the performance verification was approximately 1.12 with the, maximum was complete configuration at 1.18 without the tufts, and then 1.12 with complete configuration with the tufts. Please note that there are asterisks on the table. This is actually to represent these configurations with a 3-degree flap deflection. This 3-degree flap deflection was actually not intended, but during the construction of our model, unfortunately, the flaps did print at a slight angle and were not able to create a 0-degree flap deflection. So we were forced to test through this, and this also this probably affected our results for the CL alpha curves as well as the CL/CD curves. You'll also notice for the CL/CD curve, all the different configurations that we tested, which was the fuselage only, the complete configuration of the tufts, and then also without the horizontal tail of the empennage. All these are tabulated against each other again on the secondary screen for direct comparison. Please note that, as mentioned earlier, the aft section of our fuselage, which created a tremendous amount of pressure drag for separation, which we were not able to predict in our preliminary design analysis. It accounts for over half of our total drag, which effectively raises our CD0 value of an estimated value of 0.052 up to 0.2. This is almost a 400% increase in drag.
Sorry, say that again. Why, you just said why that was?
From the pressure drag due to separation that we were not able to predict from the aft section of the fuselage. Because as actually you can see on the primary screen, the small black line that is barely visible, it accounts for over half of our drag. Next, we were able to take these new drag values and we were able to plot a new aircraft drag polar for the total configuration at 10,000 feet. These are plotted at 10,000 feet because this is where we originally anticipated being able to cruise at, even though our intercompany proposal required us to only cruise at 6,000 feet. The L over D max value was able to be obtained for this at 10,000 feet for only 44 knots. At this speed, we do not meet CFR requirements, and we do not meet the intercompany proposal of 50 knots, being able to cruise at least 50 knots or greater. So this is one of the main challenges that we're needing to overcome in the modification of the aircraft in the next phase. Again, representing the new drag values, the power clocks were replotted, and they are shown against the preliminary design analysis that we predicted for the 10,000 foot cruise condition. Our minimum power required is only 38 knots, which effectively is almost unattainable because our stall condition we predicted to be at 34 knots. So essentially this aircraft at this point in time during the design process would not fly efficiently and would not be able to meet any of the requirements that were imposed upon us. So with the new CL and the new Q limits, we're able to reconstruct the BN diagram. You would notice a significant decrease in the Q limit velocities from the right to the left-hand portion of the primary screen. And the cornering velocities are tabulated on the secondary screen compared to the preliminary analysis and then what was found from the wind tunnel analysis of the original model. I'll now hand it off to Cassie Lipke for the stability analysis.
Thank you, Mac. Like I said, my name is Cassie Lipke. I'll go over the stability analysis for the DS-900. The first thing I want to focus on was directional stability. The aircraft is flown by inexperienced pilots, so we want the aircraft to be very stable. Our preliminary design, we estimated a value of 0.0645, and it actually turned out to be much more stable than that. We estimated this was most likely due to that pressure gradient again, and it was about a 25% difference, and our value ended up being about 0.0859. We also want to be laterally stable. Our rolling moment due to our side slip. We estimated a value of negative 0.02 due to Roscoe's recommendations. But again, we were much more stable than that, which we found satisfactory. And we were at a value of negative 1.89. And we figured this was satisfactory due to the large size of our ailerons. Our longitudinal stability was our main focus. We wanted the aircraft to be statically stable at all points. So it's important to note here that our aircraft is actually stable without the wings or the tail on. And this was mainly due to the wheels. And the value is much higher than in preliminary results, but that's because the wheels were not actually accounted for in the preliminary analysis. So the addition of the wheels added a large pitching moment, and therefore our pitching moment was actually negative 0.93 compared to the preliminary analysis of negative 0.39. This increased our static margin quite significantly. Our initial estimation was about 14%, and it ended up being about 36%, and that accounted for about 61% difference. And I'll hand it off to Kevin Garcia for model modification.
Once again, I'm Kevin Garcia. I'll be going over model modification for the DS-900 based off of our previous results. So like Mac was saying, we have a lot of drag. We need to figure out how to get rid of that drag. Like you can see on the bottom picture of the primary screen, the large adverse pressure gradient coming off the backside of the fuselage there. So our goal was to decrease that pressure gradient by making a more gradual slope from the aft of the fuselage to the start of the empennage there on the primary screen. Our next modification, once again, was related towards drag. A lot of short takeoff and landing aircraft utilize Horner wingtips to get rid of some of the wingtip vortices as opposed to winglets. The Horner wingtips, they increase the overall aspect ratio by 10 to 15% while decreasing the wingtip vortices. Assembling our modified model, basically we cut the back end off the airplane and reprinted the new aft section of the fuselage. We used 6 1/8-inch pins along with epoxy to secure the new back end of the fuselage on the existing fuselage. As you can see on the primary screen, the old model and the new printed fuselage on the lower picture. And on the secondary screen, we have the overall completed model with the new modifications. The Horner wingtips themselves were just slid off, and the old wingtips were slid off, and the Horner wingtips were slid on. That's based on the modular design that we built before. And yeah, that's the new completed modifications on the model. I'll hand off to Caleb for modification performance analysis.
Thank you, Kevin. As he stated, I'll be going over the modification of the new model performance analysis. So again, we start with the same picture on the primary screen. Comparison at 0 degrees angle of attack with the same test section wind tunnel speed of approximately 22 feet per second, which provided laminar flow still over the top surface of our aircraft. And again, with the tufted model and complete configuration, You will note on the aft section of the fuselage, there's significantly less motion in the tufts, which we're very pleased to see. However, on the lowest portion in between the wheels, there's still some movement in the tufts that created some blur and with the photography, and we attribute this mostly to the mounting of the aircraft onto the balance, and where the balance interferes with the airflow going over the aft section of the fuselage. Now, at 19 degrees angle attack, we're able to see the stall characteristics forming on the top surface of the wing, with these separation bubbles once again forming at the root and progressing out towards the tip, which was as expected. The flow is still attached on the horizontal tail, and which is good for the pitch authority during stall characteristics. And then we saw and then this is the top view of the 19-degree angle of attack, where we saw the stall conditions, where the most of the stall characteristics are again towards the root and progressing out towards the tip. And you can see moving forward to aft, the horizontal tail flow tufts are still straight and are not reversed, so therefore the horizontal tail is still flying. Now at 22 degrees, we see the angle attack that the horizontal tail becomes blanked out, and there are significant separation. There's significant separation on the top surface of the wing. However, towards the tip, where we do have the new Horner tips, there is a little bit of attached flow still. However, not as much as we were anticipating. Now with this new modified model, we reconstructed the CL alpha plots again and compared them against the preliminary design analysis results. The CL alpha plots from the new model to the original model are almost identical. Essentially, the stall characteristics changed a little bit with the new and old wingtips. However, the CL max remained just about the same, and the Alpha CL max actually decreased slightly from the old model to the new model. Now, with the major effect that the modification had on our aircraft with the new fuselage. The fuselage that we put back on there or redesigned and put back on there effectively decreased our parasitic drag value by approximately half. This was very good news to see, and we were able to then compare this against the preliminary design results, and then also, as you can see above on the primary screen, against the original one. And the one thing to note as well, which was not expected, is the induced drag with the new wingtips versus the old wingtips was virtually unaffected. We were expecting a reduced amount of induced drag at the higher angles of attack and the higher value CL, but we did not see that with the data that we received. Again, the aircraft jet flow was recreated at 10,000 feet. We were able to tell that the L/D max, velocity for L/D max significantly increases well towards a value that we're able to now fly at and meet specifications. So for 10,000 feet, we now fly at approximately 68 knots, and this is a sufficient and value that is over the 50 knot minimum requirement. And then again, the power clause for 10,000 feet. All the three preliminary design and the modified and then the original design tested are all plotted against each other. The minimum power required, which we will be flying at to meet our minimum endurance requirement, has been increased to 60 knots at 10,000 feet. So this is very good news, and we're able to meet that requirement. Next, the VN diagram was reconstructed. Our Q limits did increase. The load limit factor is no longer at 3, however it is at 4.4. We upped the load limit to, once we were doing the structural analysis, and we were able to increase then our quartering velocity So therefore, we can go ahead and so we can corner out the higher spears. And now I'll hand it back to Cassie Luke for modification stability analysis.
Thank you. I'll be going over the modification stability analysis. Like I mentioned before, the aircraft was stable for the original results, so we weren't really looking to change anything. We wanted to see what our changes did do to the stability of the aircraft. Our CM beta actually did increase slightly, and we figured this was mostly due to the added aspect ratio of the wings and the more surface area on the aft part of the fuselage. This created more of a yawing moment, and it increased it by about 6% from the original model. CL beta also increased or actually decreased just slightly. We think that this was due to the larger aspect ratio of the wings and the wingtips, and it decreased by about 6%. Then CM alpha actually went up just a hair. We think that this is due to the larger aspect ratio of the wings and the fact that there was a little less drag on the backside of the fuselage. An important note here that actually we did run into a little trouble. The trim angle, as you can see on the primary screen, looks to be about negative 15 degrees. This will be something we'll have to look further into. The original model had a trim angle of about negative 7 degrees. So this was something that really concerned us, and we will talk about in our conclusions. And I'll hand it off to Mike for structural analysis.
Thank you, Cassie. Michael, like you said, I'll go over structural analysis. Here is the flight envelope with some dust lines on it, and notice that the structural loads are 4.4 Gs for maximum, for positive Gs and negative 1.76, and the Vmax, the maximum velocity is approximately 95 at sea level. Here's the basic structural layout of the aircraft with the fuel tanks highlighted in red in the most inward point of the wings. Each one contains about 7.5 gallons of aviation fuel for a total of 15 gallons. And the green box in the center is a ballistic parachute, which will be talked about later. Breakdown of the materials of the aircraft. The green is the fiberglass composite. The plastic, blue, is a laminated acrylic, or in other words, plexiglass for the window. The propeller is made of carbon fiber, and the wings and horizontal tails and control surfaces are all aluminum. The wing structure, as seen on the primary screen, is composed of ribs and spars. The spacing and dimensions of them are on the table on the secondary screen. All the material for these is aluminum 6061 T4, and note that the spars do contain a cross-section of a seat channel, and so do the ribs. The wing deformation, analyzed in ANSYS, note that above on the primary screen, the deflection starts at half span. This is due to the strutted wing. It was assumed there was no deflection until after the strut going outwards. And the maximum deflection was displayed at about 1 inch, which is satisfactory. On the secondary screen, you can see the stress of the wing, and most of the stress was encountered at the strut, and the maximum stress was 18,000 psi, which is good because yield strength of aluminum is 21,000 psi, which means that there's really no permanent deformation of the wing. For the horizontal tail structure, you can see on the primary screen, and also the dimensions of all the spars and ribs seen on the secondary screen next to me. For the structural analysis, we did the same for the horizontal tails of the wing, except there's no strut, and the maximum deflection was only 0.03 inches, which is almost no deflection. It's not, you can't even see that. So it means that it's a little over-engineered. The spacing of these ribs are 14 inches, which was suggested to be about 30 inches, but decided to put an extra rib in there. We weren't sure because it's a control surface. And then for the maximum stress, is at 11,800 psi, which also is plenty below the 21,000 psi of the yield strength of the aluminum. For the parachute, as on the primary screen, you see it's a BRS soft pack system and it's rated for a maximum 1,050 pounds, which our aircraft only is 900 pounds, so it falls within that. It can be deployed at a speed less than 130 miles per hour. You can only cruise at a maximum of 95 at sea level, which is fine. It only weighs 24 pounds. It'll be positioned above the cockpit, as seen in the previous pictures. And then on the secondary screen, you can see the way it deploys. It'll blast out of the top with a thin layer of fiberglass, and then deploy and bring the plane safely down. Know that this aircraft on the secondary screen is not our aircraft. This was taken from Cirrus. On the primary screen is the final model, as you can see up front here. I know that the wingtips are on it, which we talked about, discussed later. And then on the secondary screen is a 3D with dimensions. Now we go over to cost and labor analysis. So that, using the RAND method and then modified for today's value, it estimated its aircraft to be manufactured for a cost of $115,000. This was significantly greater than $25,000 we were supposed to have the plane be sold for. But this also takes into account this plane will be ready to fly from the manufacturer. So the $25,000 is unrealistic for an actual ready to fly aircraft. So with a 10% margin, that comes up to $126,000. We suggest maybe having a home-built aircraft to get the cost down. Labor hours, as seen behind me, start off slow. There's a few buckets because of lag time between printing. And then on the secondary screen, it's a breakdown of hours and the cost of engineering, which takes up most of it inherently because it's an engineering course. And the phase 3 Gantt chart behind me is a breakdown of who did what on the team and when. And now I'll go to conclusions. So the wind tunnel mount caused a significant amount of drag behind our model. We suggest mounting it, raising the mount up to get that, hopefully to get that away and get away from that separation behind the aircraft and get less drag. And then the pitching moment of our aircraft is, with our pitching moment currently, we have to trim it at negative 15 degree angle attack. That is absurd, and we wouldn't be able to overcome that kind of drag during cruise. So there could be an incidence angle applied to the horizontal tail for the final test article that will help have a lower trimming angle attack, so it'll be less drag during cruise. The structure is a bit stronger than expected, especially in the horizontal tail. We can take out some of this ribs in the horizontal tail, reduce some weight, reduce some cost. That will help us there. We met the required weight, cruising, and endurance for our specifications, but we did not meet the takeoff, ground roll, and cost requirement. But as I said, the ground roll, we do take off, I think it's about 290 feet right now, which is comparable to similar aircraft today, and it will be able to compete with the aircraft. And for the cost, this aircraft could be sold as a kit plane for significantly less than $115,000. Thinking around the price, we'll be able to get it down to about the $25,000 for the requirement. And here's some references. And that concludes the presentation. Questions?
That's a story behind the picture.
Yes.
Can you guys hear me? Okay. At one point, somebody mentioned that they expected less lift in the tunnel than that they had predicted, but I didn't understand why. Could you explain that?
That out to our name system.
Less lift in the tunnel. Actually, we're expecting a lot more lift to be produced because of our fixed leading edge slots and also the design of the slot. Unfortunately, we researched that as much as we could, but we do not think that we optimize that to our aircraft. I attribute that also into the design of the fixed leading edge slot not being ideal, so we weren't able to produce as much lift. And then also that's actually, for the most part, the main reason that I would attribute it to. and that affects the flow of the wind greatly, especially whenever we're trying to maintain the land airflow characteristics that our aircraft most likely see in low condition.
Do you have any idea about how well that would scale the slotted flaps in the wind tunnel versus?
I'll hand it off to Kevin.
Okay, we did experimental aerodynamics course on leading edge slats a few semesters back, and we found out that it did scale relatively well. However, like Russ was saying, it's a lot of proprietary information, so we're not sure in terms of how well it scaled, but it worked. You did see an increase in the effective CL for the overall airflow and all that stuff, but like I said, it's a lot of proprietary information, so we weren't too sure exactly, you know, how well it scaled.
You guys mentioned that your requirement was to be able to operate at 6,000 feet MSL, and was that just a requirement that was given to you?
Yes, the requirement was 6,000 feet, did not say MSL, AGL, or anything, so we just had an assumption of 6,000 feet MSL for a baseline of the calculations, what we did in the format.
And then you did analysis at 10,000 feet, so I'm just curious as to why 10,000 feet?
Well, when we're looking at power plants for this aircraft, we found a power plant, we found the power we needed was from a turbocharged aircraft, and we ended up having our power did not go down as the altitude went up until a certain point. 10,000 feet is the normal altitude for that turbocharger when it starts to lose pressure, so we had max power all at 10,000 feet. So we figured that would be a good cruising altitude.
Okay, that seems like a reasonable explanation that you might, you're not going to do this again, but I would have recommended you explaining that. Let's see. I thought that the analysis that you guys did just on the pressure drag in the fuselage was really good. Good experience, I'm sure, for you guys. I was impressed. And then chart 38B. How do you calculate the percent difference?
Let's go to the analysis guy.
I saw that up there, and that's why I didn't mention it. I looked at it, I was like, oh, that's, yeah, it wasn't right.
Okay. All right, that's all I have. Nice job. It seems like you guys had fun with this, and you seem to understand very well. Nice job.
I really agree that that was good. It was nice to see some fun being had throughout the whole thing. Some frustration needed. Understand. On 38A, we'll look at some of those stability and control charts in particular. What CG location is the wind tunnel data resolved around in terms of percent MAC, and how does that compare to what your preliminary design number is? Are we doing apples to apples comparisons where we're looking at, say, a 25% CG?
Let's go back, yes.
In the program that Lance Schwab created, it used the CG of the actual model. So we had to input that, and then we used the CG of the actual preliminary airplane that we calculated, and we scaled it down and inputted that into the program as well.
Okay, so it does actually give you a resolved about location,
About, yeah.
and that matches what you're looking at from a preliminary design.
Yes.
Okay, good. Glad to hear that. On slide 63, under those structural analysis parts, what load case was used for that and the horizontal tail, and why?
Oh, this was taken at, for the wing, it was at the maximum 4.4 Gs, and then a factor of safety 1.5% applied. So that was the maximum that the airplane should be subjected to during flight.
And that you said that same thing, that same case was applied to the horizontal tail?
Yeah, horizontal tail, actually, the horizontal tail was not actually applied, the 900 pounds was applied to the horizontal tail.
Okay. It's not a bad assumption. Where did the 4.4 Gs come from?
That's actually part of the CFR 23, it's utility aircraft.
Good answer. Be careful with that. I heard somebody make a comment about how that increases the cornering speed by going to that utility category. So that comes with its drawbacks too, because as you're looking at some of the load cases in particular, the positive maneuvering load is rarely going to be one of them that sizes any of your structure. Sometimes it will, but not very often. You're either going to end up in an abrupt pitching maneuver for some of the tail cases, or gust driven for things that are pretty light wing loaded or very light airplanes. All of those abrupt pitching maneuvers are done at VA. So if you push that number up, that cornering speed, you hurt yourself from that way because your structure rates may go up because your load cases have gone up. So just keep it in mind that it's typical airplane design. Everything is a compromise and an iteration. You just have to deal with it. It works fine. One question, actually more of a comment on the cost. I liked the thought process that $25K for a built airplane is dumb. It is. Your recommendation for a kit is really was a good one. You're probably still not going to get there with an engine included, but that's okay. The cost estimate that you were showing for something like this is almost exactly in line with what a Cessna 162 is. The Skycatcher is running something 125, 150-ish for a two-seat LSA airplane, so that's a nice little comparative. Good work, guys.
Good job, guys. My only question was about the slot flow that Steve already asked. It does sound like you didn't have the opportunity to study that or vary that slot as part of this. So that's where my questions were. I think you chose to have it, but it would have been interesting to have seen what that was really doing for you and if there was any changes to it. I understand the time constraints that probably was out of the picture. Other than that, good job. And I didn't think it would come in under 25K acres.
Good job. That's a big checklist for only 4 guys. I guess to touch on what AJ said, because you're reconfiguring your entire aircraft, I think I would mention, just briefly mention the process of how the CG changes, because those numbers are directly going into the mount and how it's being calculated, so it directly affects your stability verification. I mentioned you have a requirement for redundant safety systems. You're going to see that in every aircraft you ever see ever. And it may be a redundant or redundant. I mean, they really go all out on that, so that's a good requirement to have. I don't remember if I saw a budget for the whole aircraft. Did you mentioned that you had a flap that was deflected at 3 degrees. Were you just unable to reprint the wing, or did you not have the time to learn?
The flaps were replaceable, in case we want to test other configurations, but when we tried to print the 0 degrees, and it came out with a little bit of deflection, and there wasn't enough time to reprint them before we had a wind tunnel test. It would have pushed us back another 2 weeks in schedule, and then from there we would be here today.
And I guess just to be nitpicky, can you go to 33A? These are really good graphs to show, but when you have that many lines, I think when you look at it, there's a lot of things we're trying to figure out to see what lines go with what. I think it would behoove you to put, I guess, a horizontal line pointing to the places that you want to look at. So then when we look at it, we don't have to kind of try to correlate what's what and figure out what we need to see. But overall, good job.
Any other burning questions?